Damping factor might be the most misunderstood number in audio. You'll hear that you need 500 for tight bass. You'll hear that anything above 20 is meaningless. And yet, both claims can seem true depending on the system. Here's the part most people miss. Damping factor is real, it does something measurable, but by itself, it doesn't tell you what your system will sound like. In this video, I'm going to show you exactly what it controls, when it becomes audible, and when it stops being the limiting factor. Stay with me because by the end, you'll know whether damping factor is actually solving your problem or distracting you from it. All right, let's start with describing what damping factor is in very simple language. A speaker driver is not just a receiver of energy, it's also a generator of energy. Yes, we all know the sound energy part, but I'm talking about electrical energy as well. Here's what I mean. Your amplifier applies a voltage across the speaker terminals, and that causes current to flow through the voice coil. Now, this voice coil sits inside a strong magnetic field created by permanent magnets in the speaker. When electrical current flows through that coil, the magnetic field and the current interact. They create a force. It's the same principle that makes electric motors work. That force moves the cone in and out depending on the direction of the current. The cone pushes air, you hear sound. This is the part everyone understands, but here's the part that often gets skipped. That same motor can also act like a generator. Anytime the cone moves through the magnetic field, the coil generates a voltage of its own. That voltage drives current in the circuit. So the speaker is not just receiving energy from the amplifier. While it's moving, it's also sending electrical energy back into the circuit. That generated signal is called back EMF, short for back electromotive force. This is happening constantly while music is playing. Now, here's where it gets interesting. The cone has mass, and when something with mass is moving, it cannot change velocity instantly. That's basic inertia, like a spinning wheel that doesn't stop the moment you stop pedaling. So, when the music signal says stop or reverse direction, the cone doesn't instantly comply. It continues moving briefly because motion doesn't stop the instant the signal changes. And while it's still moving through the magnetic field, it continues generating voltage. That voltage drives current back into the circuit towards the amplifier's output stage. So here's the question. What does the amplifier do with that energy? And this is where different amplifiers behave differently. Some amplifiers absorb that returning energy very efficiently. When the cone tries to keep drifting on its own, the amplifier electrically resists that motion. The cone settles quickly. Other amplifiers don't absorb that energy as strongly. The cone keeps drifting longer. It relies more on its own internal mechanical friction to settle down. This electrical resistance to unwanted cone motion is exactly what damping factor is about. In other words, damping factor is just a way of describing how firmly the amplifier can control the speaker electrically. It's just the interaction between electrical energy flowing back from the speaker and how well the amplifier can absorb it. Now, before you start thinking, okay, so I need an amplifier that absorbs energy as efficiently as possible, Hold on, because that's exactly the trap. The speaker designer already built damping into the driver. The suspension, the spider, the magnetic structure, all of this creates mechanical damping. That was intentional. Some speakers are designed with strong mechanical damping. Their suspensions and motor structures control motion tightly on their own. These drivers settle quickly and store less energy. So the amplifier's electrical damping has less influence on what you hear. Others are designed with lighter mechanical damping. They rely more on electrical damping from the amplifier to control motion. In those systems, amplifier output impedance can have a more noticeable effect. So, high damping factor is not automatically better. Now, at this point, some will say maybe high damping factor isn't everything, but why not just play it safe and buy the highest one you can afford? It sounds reasonable. And in fairness, having low output impedance is generally a good thing. Most modern solid state amplifiers already have damping factors well above what is audibly meaningful in most systems. But here's the reality: once output impedance is low enough, that is no longer the dominating interaction, making it 10 times lower again rarely changes what you hear. If one amplifier has a damping factor of 100 and another has 1,000, the difference in output impedance is measured in hundredths of an ohm. At that point, speaker behavior and room acoustics will overwhelm that difference in every real system. So, yes, having reasonably low output impedance is good engineering practice, but chasing extreme damping factor numbers as a safety net solves a hypothetical problem, not a real one. If you choose speakers that are electrically well behaved and you match amplifier current capability sensibly, you don't need extreme numbers to be safe. And if you later buy a truly difficult speaker, the issue will not just be damping factor, it will be current delivery, stability into phase angle, and overall amplifier robustness. If interested, check this video for a more in-depth deep dive. The right amount of damping depends on the speaker, the room, and what you're trying to achieve. This is system level thinking. Damping factor is describing one part of an interaction, and you cannot optimize one part without considering everything else. So, damping factor is a ratio. It's comparing two things: how much the speaker resists current flow versus how much the amplifier resists current flow. Your speaker has electrical resistance. We call this impedance. An 8 ohm speaker means it resists electrical current with a certain amount of force. Your amplifier also has resistance at its output, but much smaller, maybe 0.04 ohms in a typical solid state amplifier. Damping factor is just dividing the speaker's impedance by the amplifier's output impedance. 8 divided by 0.04 equals 200. Simple math. Now, here's what that means in practice. When the cone moves, it generates a voltage. That voltage drives current in the voice coil, and the current in the magnetic field creates force that resists the motion. That's the braking mechanism. Now, the amplifier's output impedance plays a key role in how strong that electrical braking can be. If the amplifier's output impedance is very low, that generated voltage can drive more current through the circuit, more current means stronger opposing force. If the output impedance is higher, that current is restricted. The opposing force is weaker. You can think of it like a drain. Low output impedance is a wide open drain. The returning energy flows easily and the motion is controlled more firmly. Higher output impedance is a partially blocked drain. Less current flows and the cone relies more on its own mechanical damping. So, higher damping factor simply means lower amplifier output impedance. And lower output impedance means stronger electrical control. That's the concept. But as discussed earlier, that doesn't automatically mean higher damping is better. The right amount depends on how the speaker was designed. Now, here's where this gets tricky. That damping factor number on the spec sheet, it's measured into a test resistor that sits at exactly 8 ohms and never changes. One frequency, usually 1000 hertz. No music playing. Your actual speaker is nothing like this. Real speaker impedance changes constantly with frequency. In the bass region, where damping factor matters most, the impedance might be high at certain frequencies and low at others. It depends on the speaker design, the enclosure type, and how everything interacts. After the bass region, impedance typically rises as frequency increases because the voice coil is an inductor. By the mid-range and treble, it might be 12, 15, even 20 ohms. And if it's a multi-way speaker with a passive crossover, the crossover can create impedance dips at certain frequencies, sometimes down to 4 ohms or even lower. So the effective damping factor is constantly changing as music plays. When speaker impedance is high, the effective damping factor goes up. When speaker impedance is low and the speaker is working hard, the effective damping factor goes down. The single number on the spec sheet is just a snapshot under some ideal condition. Some manufacturers publish damping factor at multiple frequencies. 500 at 100 hertz, 400 at 20 hertz. This is more helpful because it shows whether the amplifier holds steady in the bass. But even multi-frequency specs cannot tell you the whole story. For example, speaker A might have high impedance in the bass region. When impedance is high, the speaker isn't drawing much current. The amplifier isn't working hard. Damping factor barely matters because there's not much energy flowing back and forth. Speaker B might have low impedance in the bass region, especially at the frequencies where it's producing the most output. Now, the speaker is drawing significant current. The amplifier is working. Energy is flowing back from the cone. This is where amplifier damping behavior becomes audible. Same amplifier, same damping factor spec. Two completely different results. With speaker A, you might not hear any difference between amplifiers at all. The speaker isn't exposing amplifier behavior. With speaker B, you might hear clear differences. Tighter bass, looser bass, more control, less control. The speaker is presenting a more demanding electrical load, and that's when amplifier behavior becomes audible. Someone can say, I swapped amplifiers and heard a huge difference, while someone else can say, I swapped amplifiers and heard nothing. They're both right. Different speakers, different impedance behaviors, so different interactions. The damping factor spec is the same in both cases. but whether it matters depends entirely on what the speaker is doing at the frequencies where it's actually working. And we haven't even talked about the room yet. The room dramatically affects what you hear in the bass, but we'll get to that in a minute, because once you understand how rooms interact with bass frequencies, damping factor becomes even smaller in the overall equation. The number is real, the measurement is accurate, but the interaction in your system is what determines what you actually hear. When you understand this, you stop chasing spec sheet numbers and you start thinking about how your amplifier and speaker work together in a system. At the end of the day, this is about control. How much electrical help the amplifier provides depends on its output impedance and how much the speaker actually needs that help. Now, here's something important. Damping factor discussions almost always turn into bass discussions. Why? Because excursion is frequency dependent. At higher frequencies, the cone barely moves. Excursion is tiny. The amount of stored mechanical energy is small, so electrical damping differences are rarely audible. But in the bass, cone movement increases dramatically. The driver is moving millimeters, sometimes much more. Now, there's real mechanical energy in motion. And when there's more stored energy, how quickly that motion settles becomes more noticeable. That's why people describe damping factor in terms of bass control, because that's where its influence becomes most audible. But even perfect electrical damping cannot fix what happens next. Quick pause here. If this explanation helped you better understand amplifier damping in general, consider liking the video and subscribing. If you're on a mobile device, click the new hype feature YouTube has recently rolled out. It helps small channels like mine reach people like you who want hi-fi demystified. And now we need to talk about the elephant in the room, literally. Your room is not neutral. It is an active participant in what you hear, especially in the bass. Standing waves and modal resonances create peaks and dips in the bass response that can easily reach 10, 15 decibels, and in untreated rooms, sometimes much more. A change in amplifier damping factor might give you a half decibel shift, maybe 1 decibel in certain narrow ranges. The room is giving you 10. So when someone swaps amplifiers and hears dramatically tighter or looser bass, several things may be happening. Yes, the amplifier's output impedance may have changed the electrical damping slightly, but more often something else is dominating. A tiny shift in frequency balance can excite room modes differently. A small change in level, even half a decibel, can alter bass perception. Moving the speaker a fraction of an inch during the swap can change low frequency reinforcement. At low frequencies, the room has far more influence than the amplifier ever will. The room makes the final call, always. This doesn't make amplifier behavior irrelevant, but it does mean you cannot evaluate it in isolation. If your room has a huge peak, say at 50 hertz, no amount of damping factor will fix that. You've got a system level problem that requires a system level solution. And this is why audiophile debates about damping factor go nowhere. Person A has an efficient horn speaker with smooth impedance running a tube amplifier with a damping factor of 10. Bass sounds fantastic, tight, controlled, musical. Person B has large multi-way speakers with complex crossovers and impedance swings all over the place. The same tube amplifier, bass sounds loose, woolly, uncontrolled. Person B switches to solid state with a damping factor of 500. Bass tightens up considerably. Person A tries the same solid state amp. Here's almost no difference. Who's right about damping factor? Both and neither. Person A's system was never exposing amplifier damping behavior. The speaker was electrically benign, mechanically well damped, probably not pushing deep bass in a problematic way. Amplifier differences were masked. Person B's system was exposing amplifier behavior at every turn, challenging impedance, significant bass output, room interaction, and the works. Amplifier differences became audible. It's interaction dependent, always. So let's get practical. Damping factor becomes more audible when several things align. First, the speaker's impedance behavior matters. Here's the thing. At the driver's resonance frequency, impedance is high, maybe 20 or 30 ohms. At that point, the speaker isn't drawing much current. The amplifier sees an easy load. High damping factor or low damping factor, it doesn't matter much because there's not much electrical interaction happening. But above and below that resonance peak, impedance often drops, maybe to 5 or 6 ohms, in the range where the speaker is actually producing most of its bass output. Now, the speaker is drawing significant current. The amplifier is working, and this is where damping factor can become audible. So the question isn't just does the speaker have low impedance, but does it have low impedance at the frequencies where it's actually doing the work? Second, not all amplifiers maintain their specs under real world conditions. An amplifier might measure a damping factor of 500 on the test bench with a resistor, but when you connect a real speaker that's pulling current dynamically, some amplifiers see their output impedance rise. Why? The power supply voltage sags slightly under load. The output stage gets stressed. The actual damping behavior degrades from what the spec sheet promised. Other amplifiers have well-regulated power supplies that hold their voltage stable even when the speaker is demanding current. These stay rock solid even when pushed hard. So it's not about chasing the highest damping factor number. It's about whether the amplifier can maintain low output impedance when the speaker is actually demanding current. A well-designed amplifier with a damping factor of 100 that stays stable under a load can outperform a poorly designed amplifier with a damping factor of 500 that degrades when stressed. The number alone doesn't tell you this. You need stable power supply, current capability, and consistent behavior under dynamic load. Now, some modern amplifiers use techniques like post filter feedback to achieve very low output impedance and load invariant behavior at very reasonable costs. If you've got a speaker with challenging impedance and you need an amplifier that stays stable, this can be a practical solution. But even then, you're still dealing with the speaker's mechanical damping, the room's behavior, and whether the bass problem you're hearing is actually about amplifier damping or something else entirely. A well implemented amplifier solves the electrical side of the equation. It doesn't solve speaker placement, room nodes, or mismatched components. So, third, room behavior affects how hard the amplifier has to work. Now, this one sounds counterintuitive at first. If the room is reinforcing bass frequencies, shouldn't that make things easier? More bass output for free? Not exactly. The room can keep bass energy hanging around at certain frequencies. So the next note is happening on top of leftover energy in the room. If the speaker also has overhang, those effects stack up and the bass definition gets worse. Better cone control can reduce the speaker's contribution even though it cannot stop the room from ringing. If the speaker itself is loose and slow to settle, and the room is also slow to settle, you get bass mush. Every note blurs into the next one. If the room were perfectly damped and the speaker's job would be easier, but when the room is sustaining certain frequencies, the speaker needs tighter control to keep the bass transients clean and separate. This is where electrical damping can help, not to fight the room, but to make sure the speaker itself isn't adding more overhang on top of what the room is already doing. Fourth, if you're driving the system dynamically, quiet background music at low levels won't expose any of this. The cone isn't moving much, energy storage is minimal, and damping behavior doesn't matter that much. But orchestral crescendos, kick drums, synthesizer bass, anything with large, fast transients in the bass, now the cone is moving significantly and needs to stop quickly. This is where electrical damping can make a difference. Damping factor becomes less audible when the speaker is mechanically well damped on its own. Sealed designs with stiff suspensions, smaller woofers, controlled behavior, these speakers settle quickly on their own, which means they generate less back EMF. There's less electrical energy flowing back to the amplifier. So even with a high damping factor amplifier, the electrical damping interaction is minimal. The speaker's mechanical behavior dominates. The speaker has smooth high impedance in the bass. It's not demanding much current from the amplifier. So the amplifier output impedance becomes less relevant. You're using subwoofers properly, taking deep bass duty away from the main speakers. The mains aren't moving large excursions, so damping becomes less critical. The room is well managed. Good placement, treatment, or EQ taming the bass properly. When the room isn't reinforcing and sustaining bass frequencies, the speaker's job is easier. The amplifier has plenty of current capability and a stable power supply. Even if the damping factor number isn't super high, stability under load conditions matter more. None of this is about being better or worse. It's about whether the interaction is significant enough to matter in your specific situation. So what actually works? This is the heart of why damping factor makes such a poor buying strategy. The spec alone cannot tell you whether this amplifier will control your specific speaker, whether it will solve the bass problem you're hearing, or whether it will sound different from what you already have. Because the outcome depends on the entire system. I see this pattern constantly. Someone reads that a damping factor is important. They look at their amplifier, see it's rated 100, and think, I should get something rated at 500 or 1,000. They buy the new amp, hook it up, and maybe they hear a difference. Maybe they don't. Maybe it fixed one thing and made something else worse. This is not because damping factor is meaningless. It's because they tried to solve a system problem by changing one component in isolation. So, what actually works? System level thinking. Start with speakers that have stable, well behaved impedance curves. This makes everything downstream easier. Choose speakers that don't store excessive bass energy or push into deep frequencies your room cannot handle. Address room interaction early. Speaker placement, bass traps, get the room right, and suddenly amplifier differences shrink dramatically. Match amplifier current capability to speaker demand. A speaker with wild impedance swings and low dips needs an amplifier with solid current delivery and stable power supply, not just a high damping factor number. When you do this, amplifier differences shrink to their proper scale. You're no longer using the amplifier to compensate for speaker or room problems. You're not trying to tune the sound with amplifier colorations. You're trying to build a system where the amplifier's job is easy and everything works together predictably. Quick aside about cables, because this comes up quite often. Speaker cable resistance adds directly to amplifier output impedance. If your amplifier has 0.04 ohms output impedance and your cables add zero point 0.2 ohms, your damping factor just dropped by a factor of 5. Does this matter? Same answer as everything else. It depends on the system. Long runs of thin cable into a difficult speaker load, cable resistance might be audible. Short runs of decent gauge wire into a benign speaker in a well managed room, cable resistance is swamped by everything else. Just use appropriately sized wire for the distance and impedance. It shouldn't be complicated. Damping factor is a measurement of a real electrical and mechanical interaction. Under the right circumstances, it's audible. But it is not a universal explanation for amplifier sound. It is not a shortcut for system matching. And it's definitely not a number you should chase on a spec sheet or your strategy for buying. If you're not happy with your bass right now, here's a simple checklist. First, identify what's actually wrong. Is it boomy, thin, uneven? Different problems have different solutions. Second, address placement and room interaction. This is always step one. Third, look at your speaker itself. Is it appropriate for the room? Is it pushing lower than the room can support? Fourth, check amplifier matching, not just damping factor, but current capability and whether the amp is being stressed. Fifth, only after all that, consider whether the amplifier damping behavior is part of the equation. Most of the time, you will never get to step 5 because the first 4 steps fix the problem. Damping factor matters sometimes, but it only matters inside a system, and in that system, the room is always participating. If you want predictable bass, start with the fundamentals. Speaker behavior, room interaction, impedance stability, and current capability. The videos on your screen will help you build the system correctly from the ground up. Click on one and I'll see you there.